Hello everyone, it's 1 p.m. Eastern Time, and that means it's time to begin another of our monthly CoCoRaHS Weather Talk webinars. Thanks for joining us today. I'm your host, Henry Regis. My regular co-host, Nolan Duskin, is out traveling on the road today. Behind the scenes, running our program are Zach Schwalbe and Noah Newman, and we're coming to you live from the Colorado Climate Center here at Colorado State University in sunny Fort Collins, and we had a lot of snow here in the last 3 days, so it's nice and white as I look out the window here from our studio. Hey, today we'll take a look at a subject that's fascinated many people over the years, and perhaps you've even seen one yourself, that being tornadoes. And we'll talk more about that as our guest Greg Carbin comes up shortly. For those of you who are unable to join us for our live broadcast today, we'll be recording this for future viewing on our website. All of our Weather Talk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, we're excited to have with us today Greg Carbin. Greg is currently the Warning Coordination Meteorologist for the National Weather Service's Storm Prediction Center in Norman, Oklahoma. And Greg has been there since 1996. A little background, he grew up in Vermont, attended Linden State College. His role is a spokesperson for the SPC, the Storm Prediction Center. You may have heard Greg on NPR or TV. He's featured in NOVA's television program on tornadoes, and we've actually put that on our website, a link to that as well. And one thing Greg does, which is really a lot of fun, he does a year-in-review presentation at the National Weather Association annual meetings every year. We're going to see if we can get Greg to come in at the end of the year, probably in November, and if he might be able to do that for us. It's a fascinating look at the severe weather or significant top 10, kind of like David Letterman's top 10 significant weather events during the season. So, well, if I've heard Greg speak at these conferences, let me tell you out there, you're in for a real treat today. Welcome, Greg. It's great to have you with us.
Well, thank you. Thank you, Henry, and it's good to be here. And you'll be happy to know I had, let me see if I got my screen going here.
We're coming on that right now. Here you go. There we go.
Okay, we're all set. Thanks
It
again,
looks like a busy day for you guys.
For inviting me to give a weather talk today. I've been looking forward to this for quite some time. And I'm a CoCoRaHS observer as well, although I haven't been all that good lately because of the long-term drought Oklahoma's been in, and it's hard, and once you get rain, you're just so excited about it. You look at what you got, but I forget to log it. This morning I had 2.32 inches of rain over the past 24 hours in the rain gauge, and both my wife and I are very excited about that because it means the gardens are going to go crazy. So good news there. Well, I'm going to speak today about forecasting the Ferocious, the how, what, where, and why of tornadoes. And I was just looking at this title, and I'm like, that's an awfully ambitious title I set for myself. So bear with me. I think that other CoCoRaHS folks on the webinar are probably weather enthusiasts, and we're going to get into the thick of the how we forecast and what we're trying to forecast, and also where. The why is also part of that. And then we'll end the talk with some technical discussions about perhaps longer range forecasting, or maybe being able to begin to attempt to seasonally predict forecasts for tornado events. So let's get started. These are some images of the catastrophic damage that occurred with the April 27th, 2011 tornado outbreak across parts of the South. This is in Alabama, and this is why we do what we do, because if we can get heads up on this type of weather, if we can get people aware that this danger exists in their area, they can take appropriate action to save their lives and protect their property. And of course, that's the role of the National Weather Service, to protect the lives and property of the American people through timely forecasts. So I'm going to talk today, a good part of the talk, about that process. How do we go about forecasting these dramatic, dangerous, and somewhat unusually and rare events? You know, they don't occur very often. It's difficult to bring the conditions together, and so you don't want to be over forecasting these events and scaring everyone. You want to get the forecast right when it really matters. So how do we do that? First of all, at the Storm Prediction Center, we do more than just tornado forecasting. We start with the basics of thunderstorm forecasting, and of course thunderstorms can result in a variety of severe weather, from flooding to heavy hail. Wildfires are also something we're concerned about here, and we do this all on a national scale. We're looking at the continental United States weather systems and how they affect the people and others in harm's way. We're in Norman, Oklahoma, based in the southern part of the University of Oklahoma campus at the National Weather Center, staffed 24 hours a day, 7 days a week. Our forecasts are distributed nationwide and are used by other National Weather Service offices across the country. You can kind of think of this as a center of expertise for thunderstorm forecasting, and that expertise is then shared with offices that may not experience severe weather all that often. If you're a meteorologist, say, in Bismarck or Billings or Vermont up in Burlington, you're not going to be experiencing severe weather all that often. And the forecasters here at the SPC are challenged with the task of forecasting hazardous, dangerous thunderstorms day in and day out, 24 hours a day, 7 days a week, and we look at the whole country. We really don't have any boundaries that restrict us. And so by doing that over a period of time, and as you'll see coming up, experience plays a huge role in the forecaster's ability to pick out difficult situations when severe weather may occur, and to share that guidance and interpretation of the weather information with parts of the country that may not experience severe weather all that often. So the forecast process, I'm going to spend some time here going through each one of these steps and how we put these steps together. An analogy to this is perhaps the medical profession. When you go to see a doctor with a particular health problem, and you're not sure exactly what that is, the doctor has to do an initial diagnosis, and in the doctor's mind there are certain problems or symptoms that are associated with different sicknesses, illnesses, and disease, and they have to do this detailed diagnosis before they can ever make a prognosis or a forecast for what the problem may be with your health. And so the analogy is similar with weather. We start with an idea of what the atmosphere can do, but we need to understand what it is doing at the present time and bring our experience to bear on that before we can even attempt to forecast what the future state will be. So we'll go through each one of these steps in some detail. We'll start with conceptual models. So for severe thunderstorms, we really need to know where can we get thunderstorms to develop, and we call this deep moist convection. And so the forecast is really to assess the potential for thunderstorm development and then to determine whether those thunderstorms could become severe or not. And what I mean by severe are organized storms, usually persisting for more than an hour, with the potential for large hail, perhaps 1 to 2 inches in diameter or larger, high winds in excess of 50 miles an hour, and tornadoes. And those are kind of the three defining features of a severe thunderstorm. Many thunderstorms never reach that level of intensity, and you'll see that in many conditions you can have thunderstorms, but they're not going to be all that intense or long-lived. We're really interested in those that are going to be long-lived and have the potential to become intense and even deadly. Of course, any thunderstorm could be deadly given the lightning it produces, but we're really interested in looking at those storms that move along and cover a relatively large area and have a higher potential for danger. So we start with an ingredients approach to forecasting, and really when we look at the tornado forecast problem or the severe thunderstorm forecast problem, it's kind of like baking a cake. The ingredients are needed to bake a cake, just like you need certain ingredients to be in place in the atmosphere in order for storms to form. And three of the crucial ingredients for thunderstorms are instability, lift, and moisture. And the definition is shown there on the slide. Instability is basically the tendency for air to rise up or down in the atmosphere, but we look for positive instability when the temperature in the lower levels near the surface is much warmer than the temperature just above the surface. And this allows an air parcel, once it's put up above its level that it's currently stable at, once you bump a parcel up into a cooler air mass and it finds itself warmer, it'll rise just like a hot air balloon. But you can't really do that without some mechanism to lift the air. And so we need to look for those mechanisms as well. It could be in the form of a mountain range with air moving up the mountain, It could be in the form of a low pressure system like you see on the weather map, or a front, a cold front or a warm front. These are features that provide lift in the atmosphere. And then finally, the fuel for thunderstorms is really moisture. And we need to look for sources of moisture, relative humidity, higher dew point air coming from the Gulf of Mexico, or even coming off plants and forests where the green up sometimes generates moisture on its own. So these are the three basic ingredients for any thunderstorm. But there's one more crucial ingredient for sustained thunderstorms that we're really looking at as far as the danger for severe weather, and that's vertical shear. The vertical shear is the fourth crucial ingredient for severe weather, and essentially that's just the change in wind speed and or direction with height. And this schematic here shows kind of the classic, what we call supercell thunderstorm. And you can see it's tilted in the direction of this, away from where the stronger winds are pushing the updraft and the precipitation associated with this thunderstorm away from the lower levels where inflow and warm moist air is continuing to fuel this convection in the atmosphere. And it's this wind shear combined with the instability, moisture, and lift that set up the right conditions and the right ingredients just in the right magnitude for sustained deep convection that is organized and long-lived, rotating storms, and eventually the potential for tornadoes, large hail, and high wind. So let's move on to diagnosis. So now we have this conceptual model of the ingredients that we're looking for in the atmosphere. Well, we need to know where those ingredients are, or if they exist on the current weather map. And so there's a lot of detailed hand analysis, believe it or not, that still goes on. And this sort of combines the observations that we get from airports across the country. And of course, the CoCoRaHS, you know what observations are all about. They're critically important to helping us understand the atmosphere, understand what's been going on in the world of weather. And so many airports across the country report hourly, sometimes more frequent observations of wind speed, surface pressure, temperature, dew point temperature. All this information can be analyzed by the meteorologist to come up with the current state of the atmosphere, mostly at the surface, but also some of the computer models assist us, and also balloon observations and aircraft observations assist us in understanding what's going on above the surface as well. And we can combine these features with things like radar imagery, satellite imagery, the IR image there with lightning information on it across the Tennessee, Mississippi Valley, and then also integrate that observed information into our conceptual model so we have a good idea of what the atmosphere is currently doing in a three-dimensional state, and then we can begin to move forward from there. And that's where experience comes in. And the longer you've been doing this line of work, it's rather exciting, really. You start to see the atmosphere repeat itself. Not exactly, but the longer you go on, the more experience you gain in events, and you can begin to get a sense for when the big days are beginning to unfold, or maybe you may have doubts about whether it will be all that big a day because of some differences in what you've experienced in the past. And I'm going to go through a couple of things here. First of all, just the basic probability of a tornado event occurring within 25 miles of any location in the United States on any day of the year. And this is just a repeating loop that goes through the entire year for every day. And it shows the probability of a tornado event within a 25-mile radius of the location. And what you notice here is a migration of that potential. It starts out in the southern United States, down along the Gulf, migrates up into the Great Plains, the northern plains, diminishes, and then returns back to the Gulf Coast states during the later part of the year around December. The other thing to notice here is the highest probabilities are not very high at all. In fact, they max out at just under 2%. That's a 2% probability for May, let's say late May, early June day in northwest Kansas, northeast Colorado. A 2% probability of a tornado event within 25 miles of a location up there in northeast Colorado at the beginning of June. That is a very low probability. And essentially what that's showing us is that tornado events are unusual and rare. They do not occur very often. But when they do, they tend to occur in proliferation. And when the big events occur, they can be incredibly destructive. Here's another way of looking at that map, just showing the monthly the maximum month of when tornado activity is at its maximum. And again, you see the November time period down there on the Florida Panhandle, moves up into the Tennessee and lower Mississippi valleys through April, and then moves up into the plains through May and June. Late June and July, you're all the way up into the Arrowhead of Minnesota, North Dakota, and also on the East Coast you see a maximum tornado potential around the Washington, D.C. area. And then it'll begin to recede again as you go into the fall. What's kind of interesting is there's always a low-end probability near the Gulf where the moisture is available. Throughout the year, there's this low-end potential that exists there. But in many other areas of the country, this potential will come up pretty dramatically in the springtime and then drop off through the summer. Another part of experience of these events I just talked about, these dramatic events when all the ingredients come together for particularly disastrous days. Oh, one other thing I want to talk about here before we get to that is why are the Great Plains so special? And we see a lot of events. I'm getting a call here. Sorry about that. I'm sorry, I can mute my phone. Why are the Great Plains so special? Well, we have two features in the continental United States that set up an environment very favorable for severe weather and storms. One, the Rocky Mountains, and the other, the Gulf of Mexico. And it's the juxtaposition of this topography that allows for the elements or the ingredients we just talked about to come together in particular intensity across parts of the Central Plains. Excuse me a minute, I'm sorry about that. This is Greg Carbin. Yes, I'm on a webinar, sorry. Okay, yep. Yeah, that's fine. Yep, that's fine. Yeah, bye. Very sorry about that. Can't help it, I'm in my office, so phone rings. So back to this. The Central Plains are a place where you can bring the ingredients together because of the topography that exists across this part of the country. And this is actually unique on the planet. There is no other place that has the extensive setup that we see here in the central United States with the Gulf of Mexico juxtaposed to the high terrain to the northwest. There are regions with smaller areas of potential for tornado events, but this is the largest spatial coverage of this type of topography anywhere in the world. And that brings together the warm, moist air again from the Gulf of Mexico, the cold, dry air from off the Rockies and the high plains. You bring those two air masses together in just the right way with strong winds aloft, and you can set up the favorable environment for a rotating updraft in a thunderstorm, what's known as a supercell. And there's a picture of one. Another thing about pattern recognition is an experience. The atmosphere doesn't exactly repeat itself, but it does tend to come close to what it's done before. On the left here is a forecast, a two-day forecast prior to the April 27th, 2011 event in the southern United States, and a match for that forecast from November 10th, 2002. Well, on November 10th, 2002, there was a pretty significant tornado outbreak across parts of the South and also across the Midwest. Over 83 tornadoes with that event, one of them an F4, and a number of fatalities, 36 in all, almost half of those occurring in Alabama. So this kind of gave us a bit of a heads up. You know, the atmosphere is coming into a configuration where it has produced significant severe weather before. We can feel more confident in our forecasts and really ramp up the wording in terms of the danger of this system. How about some other events? Well, one of the more significant modern memories before 2011 was the April 3rd, 4th, 1974 super outbreak. Over 100 tornadoes in 24 hours, over 300 fatalities with this event. In some ways, similar to what we saw on April 27, 2011, but in other ways, different. No system is going to be identical to another. But this event really held the standard or the high bar for tornado outbreaks in the United States up until 2011, when it was probably matched, certainly equaled in its intensity on April 27, 2011. Going back a little farther in time, here's the Worcester tornado from June of 1953. And this is actually the culmination of a three-day tornado outbreak that started out in Texas, continued up into the Great Lakes region, and then on the third day, even into New England. Over 500 fatalities associated with this outbreak, and quite striking to see a tornado of that intensity across parts of New England, Massachusetts. And interestingly enough, also in 2011, early June, which is the same time that this Worcester tornado occurred, we saw another significant tornado hit the city of Springfield, Massachusetts, kind of an eerie similarity in some respects, but not as intense a tornado event, thankfully. And then perhaps one of the most dramatic events in tornado history in the United States is the tri-state tornado, March 18, 1925. This is the single deadliest tornado in U.S. history with over 700 fatalities. It was a long-track, violent tornado over 250 miles from Missouri into Indiana. Not a lot is known about this, and not a lot was known about tornadoes then, and this came very suddenly during the daytime, and people had no warning, and many lives were lost. So bringing it all together now with what we know, well, one thing, just looking at those more significant events, you might realize they don't occur all that often. In fact, 25, 30 years between some of the more significant tornado outbreaks. So that really talks even more about the importance of experience. You really need to have a long period of historical record in mind when you're trying to forecast some of these bigger events. We use the forecast funnel to approach the problem, and really we're looking across time and space scales here. Large-scale weather systems first, assess where they are and what they're doing, and then the fronts and rain bands that are associated with those larger scale systems and how those are driving smaller scale thunderstorm events, the ingredients we just talked about, and then ultimately what's the potential that some of those thunderstorms could result in tornadoes. So this forecast funnel process or concept is used by meteorologists to go from the big scale to the small scale and try to get, capture everything that's going on. The complicated factor in this is that there's interactions between these scales, both from the upper levels and large scale to the small scale, and up from the small scale to the large scale. But as an example here, graphically, here we're looking at part of the northern hemisphere, large-scale weather systems traversing from the Pacific from west to east across the continental United States. These waves in the atmosphere drive vertical motion. That's the lift we need. And this is a really large-scale look. We see basically 3 weather disturbances here, one across the middle of the country and another one coming into the Pacific Northwest coast. We drop down now in scale, and we see that middle system there, and one in the middle of the country is driving a low-pressure system across parts of Kansas and Oklahoma. We assess the winds in that system, what the moisture is doing, how it's being brought into the system, where's the lift occurring, where's the stronger wind shear with this, and where is the best area for thunderstorm and tornado development at this scale. And then we'll drill down a little bit more, our conceptual model for thunderstorm formation. What's fascinating to me is how you see the similarity on different scales. So here we're looking at a low pressure system associated with a supercell thunderstorm. That's not the same That's not the same low pressure system that was on the map there in the central U.S. This low pressure system is a larger scale one than the low pressure system associated with the supercell. But they're similar in nature, and the conceptual model applies. Where you see low pressure, you've got air moving toward that low pressure. It can't go into the ground, it has to go up. So low pressure is definitely a form or location where lift is occurring in the atmosphere. And then finally, is there sufficient shear and organization to the thunderstorms that they could produce long-lived rotation and a tornado forming and hitting somewhere on the ground. So we're assessing these ingredients and these environments across different time and space scales. And it's a pretty exciting line of work, but it can also be very frustrating at times because some of this information is not always available. A lot of information comes from computer guidance, especially now with the faster computer systems allowing us to run many different simulations of the atmosphere. And these models are run what are called the primitive equations, and computers are ideal at crunching a lot of numbers really fast. And nowadays it seems like not a week goes by where we don't have another form of numerical guidance to refer to. And we're getting now at the scale in these models where they can actually simulate thunderstorms. When I started in meteorology 25 years ago, that would have been a wild dream. But now we have computer models that actually simulate thunderstorm development. And that has allowed our forecast to improve. Here's the April 27th example here The forecasts at day 5 were beginning to indicate a risk across parts of the Arklatex east to the southern U.S. The day 4 really concentrated across the Tennessee Valley up into the Appalachians. We went with a moderate risk on day 3. That doesn't happen very often, up to a high risk on day 1. And then you see the reports that occurred on that event overlaying the risk areas. So it's a combination of experience, ingredients-based approach to forecasting, computer models, all brought together and brought to bear on this problem that has resulted in remarkably good forecasts for some of the more significant events. And so the forecast funnel here I'm going to apply to the products that the Storm Prediction Center issues. And when we're talking about large-scale weather systems, we're really talking about severe weather outlooks. And we're talking about the large-scale aspects of these systems and how they will affect the potential for severe weather over areas, a few states in size. We get down to a few hours, we're looking at more detail again. The smaller scale ingredients that go into severe weather development and sustaining severe storms are discussed in these mesoscale discussions that are written at the SPC. And then finally, the decision of whether to put an area in a watch. And a watch essentially means keep an eye out. We think conditions are now either very close to or becoming favorable for the development of severe storms, or severe weather is moving from one area to another, and a watch will be issued. The Storm Prediction Center really specializes in the top of the funnel here, right down to the issuance of the watches, and then ultimately the warnings are issued based on whether storms form and are shown potential to be dangerous on radar. And those warnings are issued by the local National Weather Service offices across the country. So let's review a little bit more about what we mean by watch. There's a tendency for some confusion between the wording, but it really shouldn't be all that difficult to remember. A watch means what it says. Watch out. You know, conditions in your area could become favorable, and keep an eye out for that development. It hasn't occurred yet in most situations, but it looks likely that it could. And so these are issued, the watches from the Storm Prediction Center, the watches that you see on the Weather Channel every spring and summer, originate here in Norman, Oklahoma with meteorologists at the Storm Prediction Center, and they're based on forecasts and observations. And we hopefully get those out with some lead time prior to the significant events. And when we say lead time, I'm meaning maybe 1 to 2 hours ahead of the warnings. Here's an example of the number of watches issued per year for tornado watches. If you live along the Gulf Coast, you may see up to 20 watches a year in that part of the country. Now, we also issue watches for landfalling hurricanes and tropical weather systems, and so that part of the country is particularly vulnerable to tornadoes, not just in the springtime months and even into the winter, but with tropical storms and hurricanes making landfall in that part of the country. As you move toward the plains, the frequency of tornado watches drops off somewhat. You may see on average 10 to 12 tornado watches a year in the plain states. Much fewer issued across the Rockies and West and extreme northern parts of New England. Severe thunderstorm watches are a little more common than tornado watches and really concentrated across the middle part of the country. Again, there's that favorable zone for the conditions we just saw with the Rocky Mountains and the Gulf, setting up the favorable conditions for severe weather. Not always tornadoes, but large hail and high winds, not uncommon across that part of the country, the central and southern plains, for much of the year. You also see, if you look real closely, an extension in that watch frequency across the Midwest, parts of Iowa into Illinois, Indiana, and even Ohio. And that's kind of a corridor that will see activity throughout the summer months in the form of what we call derecho events sometimes, or maybe just somewhat organized, longer-lived thunderstorm complexes called MCSs, or mesoscale convective systems, move across that area on a regular basis during the summer months. And so that's why you see a bit of a peak there in the number of severe thunderstorm watches. And in that area, we're talking on average 15, 16 severe thunderstorm watches by county per year. So you can pick out your location or the county that you live in and see if these maps hold true. They're based on 20 years of data, so they're kind of a smoothed average over that period of time. How about warnings? Well, once a warning is issued, there's really not much else left to do except take action. And so warnings mean that the storm has shown its hand and is certainly looking as if it could produce or is producing severe weather, and you need to take action right away to protect your life and property. The danger is immediate. The certainty is relatively high. These are based on radar observations and or reports of damaging weather or tornadoes. And here's just a look of average tornado warnings for the period. This is an annual average for the period 2002 to 2011. And there's some interesting aspects to this map. You don't see the classic tornado alley. In fact, you don't see the max at all, where we just saw the severe thunderstorm watches issued across Kansas and Oklahoma. But again, these are for tornado events. You do see an awful lot of tornadoes across parts of Mississippi, tornado warnings across parts of Mississippi and Alabama. In fact, some of those counties, upwards of 6 tornado warnings on average per year. Now, some of this is due to big outbreaks that have occurred in that area, especially the 2011 outbreak. And you kind of get this idea that, you know, there's this southwest to northeast corridor of potential there where tornadoes have been more common during this period of time than at others. And then in the high plains, there's another maximum from northeast Colorado across northwest Kansas and into Nebraska, where you see tornado warnings maybe get up to 2 to 3 tornado warnings in those counties per year. The rest of the country, pretty rare for tornado warnings. Now, a warning is a very small area. It's just trying to encompass the area that the tornado is going to impact. And so there's a big scale difference between the watches that we just looked at and the warnings. More information on watches and their relationship to warnings is available on YouTube. If you just go to YouTube and type in "What's a Watch," you'll get the YouTube video that we produced here at the Storm Prediction Center last year, and it's a very informative, short, less than 3-minute piece on what we do here and how we issue watches.
Greg, I've put a link to that on our website as well, so folks can go right there.
Great. So let's transition now. I think I've really hit the forecasting and the products that are issued by SPC pretty heavily, but I want to talk to finish out where we are so far this year and where we might be going with tornadoes specifically. So this chart shows us the annual cycle of tornado events. These are all tornadoes across the continental United States, and we've adjusted it somewhat because we're getting more reports than ever before. It seems very unusual for tornado events to go undetected now in much of the country, especially this part of the country where people seem to want to chase them. There are many, many more reports in the modern era than there were, say, back in the 50s and 60s. So we've tried to make an adjustment for that here, and we think this is a relatively accurate depiction of the current number of tornado events in the United States as we go through the year. The black line is this year up until just a few days ago. We had a few tornadoes yesterday, so we might bump that up now to maybe 175 or so. But what you see is we started out the year 2013 very active. January had an outbreak toward the end of the month that boosted the total up to about 100 or so, or maybe just under 100. February, a few scattering of events there. March was almost flatline, very few events in March. And we started to pick up again here a little bit in April. However, the month of March really kept us below normal. We dropped below the green curve, which would be the median expected value for the month of March, toward the end of March. And we're having a tough time catching back up to what would be considered average number of tornadoes. At this point, we're still running well below average for the number of tornadoes through 2013, and that's just fine by me. So, I mean, it is interesting to forecast these, but I would much prefer fewer than more. So what about March? It was very interesting to see that the month of March in 2013 had the fewest tornadoes since 1969. And so I was sitting at home one evening and I said, well, that's kind of an interesting fact. And I wonder what March of 1969 looked like compared to March of 2013. Well, I did that. It's easy enough to do nowadays with the modern reanalysis available from various outfits of NCAR and NCEP reanalysis data. So on the left is the upper level pattern for the month of March 1969, when only 8 tornadoes were recorded in the United States, the fewest in 60 years of data. And basically the blue just means that the pattern is colder, or the heights at the 500 millibar level are lower, anomalously low. And you've got a lot of cold air that's coming into the United States from Canada, and it's moving across the Midwest and across the South and even across parts of the Gulf Coast. And sure enough, on the right, you see the very similar pattern for this March of 2013, when we only experienced 14 tornadoes. Very, very similar patterns for these Marches. And essentially what this shows is that the cool air in March tends to suppress tornado activity. If March has below normal temperatures, especially in the central and eastern United States, that tends to suppress the moisture, keeps the moisture from returning to the continental U.S. landmass, and that really is one of those critical ingredients required for thunderstorms and tornadoes. So this is the type of pattern you would expect with very few tornadoes, and that's indeed what we saw. The question then becomes, can we forecast this? Well, the NOAA Climate Forecast System model issued this forecast in the lower right at the end of February 2013. So we could have perhaps said something at the beginning of March that if this forecast holds true, these below normal temperatures and below normal heights that we see over the eastern United States, especially anomalous for March, could keep tornado activity at a minimum. And that's indeed what happened. So maybe we're heading in a direction where we might be able to begin to talk about seasonal tornado forecasting. It's very much in its infancy, but that kind of makes it exciting too, because we're on the cutting edge of this potential. I'm going to get a little more complicated now, hopefully not too much. Put your seatbelts on. To talk about temperature anomaly and tornado numbers by month. And so the stars on this chart are essentially the average number of F1 and stronger tornadoes in the United States per month over the last 60 years or so. And so you see January, February below 25 average, and then we go to March, we're maybe 30, and you peak in May here at just over 100 tornadoes, F1 and stronger, for the month of May. Also on here are the monthly tornado counts for the 10 coldest months and the 10 warmest months in any year of these 60 years. And the bars are essentially the average of those cold months and warm months. And so what this depicts here is during the month of March, and we just saw that, if you're seeing below normal temperatures, you're seeing below normal tornado numbers. And that's what we see. We're below, the blue line is below the star. And so below normal March temperatures usually result in below normal tornado activity. Not always. You see a peak here where it didn't quite match up quite nicely. And what's fascinating about this is April is very noisy. You really can't say too much about above or below normal temperatures and tornadoes in April. And then we switch. When we get into May, it's the colder months of May that actually end up producing more tornadoes in the United States than the warm months. And we see this type of pattern continue through the summer. So if it's a very warm summer, like we saw the last two, the numbers of tornadoes are fewer than we might expect in a normal or cooler than normal month of May, June, July, August, and even into September. So the summer months and into the fall, early fall, if it's cooler than normal across the continental United States, or much cooler than normal, it may mean we see more tornado activity. On the other hand, if it's much warmer than normal, especially in May and June, that kind of shuts down tornado activity. And we think we know why that is. I mean, in order to get warmer than normal conditions in the continental United States, you need a large ridge of high pressure over the central U.S., eastern U.S. And with that high pressure in place, you don't have the critical ingredient for organized severe thunderstorms, and that's wind shear. So when we see warm conditions develop in the spring and especially in the summer, the wind shear is non-existent, and so are the tornadoes. So here's our outlook for May through July 2013, and it looks like we see a pretty high probability of above normal temperatures. This forecast was issued almost a month ago, so they don't issue them all that often. It could change with the next update. But right now, a large part of the United States is forecast to experience well above normal temperatures as we move into the summer months. I'm not happy about that because I've seen enough hot summers here in Oklahoma, and I think parts of the Southwest won't be too happy with it either because warm weather also brings dangerous fire weather conditions. But if this is indeed verified as a forecast, look for the likelihood that tornado activity will be below or slightly below normal, so that the trend that we're currently seeing in below normal tornadoes in 2013 is likely to continue if this forecast is correct. I think that's just about all I've got. Well, there's our below normal activity for warmer months. I did want to give a quick plug here for the new Storm Prediction Center website, www.spc.noaa.gov. Major redesign, just previewed or debuted a few weeks ago. If you haven't been there yet, there's just so much information you could spend days trying to figure out what you want to look at. But it's a great redesign. We've gotten a lot of positive feedback on it so far, so have a look if you're interested. A few folks to credit here with the talk. A lot of people helped with the content of today's presentation, and I want to recognize them. And I do want to go over the questions that we asked in the survey for those who signed up for the webinar. So let's take a quick review of the Q&A that was sent out and give you the answers on that. Should you open windows in your home if a tornado is approaching? Believe it or not, my wife asked me this last night, and it wasn't really a big threat of a tornado. And I said, you know, let's just shut the windows. It's getting windy out there. And she said, oh, shouldn't we leave them open? And I said, now, where did you hear that myth? It's false. The tornado may have very low pressure associated with it, but the winds are probably going to cause more of a problem, and opening your windows is probably not going to make much of a difference. So the better thing to do is stay away from windows, get to an interior room away from windows, and hunker down if the tornado is approaching. Question 2, what's the average number of tornadoes in the U.S. each year? Well, I've sort of covered that in that graph, but it's roughly 1,300, but it can range dramatically from one year to the next. That's one remarkable thing, is you have this dramatic variability in tornado numbers from one year to the next. But if you average it all out, it's probably about 1,300 tornadoes a year. Can tornado winds reach over 200 miles an hour? Yes, certainly. Not uncommon in the strongest, most intense tornadoes, and in fact, radar data has remotely sensed tornado wind speeds above the surface in excess of 300 miles an hour. What months of the year have the most tornadoes in the U.S.? Well, usually it's going to be May and June that are the most productive, although sometimes April turns out to be the busiest month for tornadoes. In fact, 2011 was one of those years in which April had more tornadoes than any other month. But usually it's going to be May or June. And can tornadoes form over mountainous terrain? The answer is yes. And I think it was a Wyoming tornado at over 8,000 feet. I think there may have recently been last year a tornado documented in the Rockies, well over 8,000 feet. So terrain has some impact. Obviously, you're not going to see the most unstable conditions high up in the mountains, but tornadoes can form just about anywhere, given the right conditions. And they have formed in every U.S. state. So that, I think, covers it. Those are the questions we asked with the webinar. I appreciate your attention today, and I thank CoCoRaHS for inviting me to give the talk. And I'll take questions now, I guess, from the audience.
Greg, thank you very much. We really appreciate your time today. These are a very fascinating look at the forecasting and the ingredients with the storms. Just to let you know, we have put the Storm Prediction Center website on a link to the website on our web page, and actually we're going to be running a message of the day for the next couple of days on SPC, so folks can link and take a look at that as well. I got a quick question for you. Is there an event in your life as far as tornadoes go that made you go into this type of work? Have you seen one?
Up in New England, there were very few opportunities to experience tornadoes. For me, it was winter storms. I loved Vermont winter storms, and I just became fascinated with the aspect that that Mother Nature could have such an impact on mankind that, you know, the power could go out or school would get canceled, and so I became interested at a fairly early age in weather because of its impacts and what appeared to be our inability to make any difference in that. But now I know we can make some difference if we can forecast it.
Thanks. Well, we're going to take questions now. If you would type in your name and the state you're from. We've got about a half an hour, so we're going to try to get as many questions in as we can. And one of the questions that just came up, Laura from New Hampshire, of all places, says that sometimes there's tornadoes in southern part of the state. And, I remember tornadoes in western Mass, Stockbridge, Barrington, southern Vermont, northwest Connecticut. Her question is, what causes those? Is it similar between the Gulf of Maine and the Appalachian Mountains as the Rockies and the Gulf of Mexico?
Very similar. In fact, what we saw today in the talk were the areas where they're most common, but there really isn't anything restricting those ingredients from coming together in other areas of the country. And so really what you need to think about is that that conceptual model that we have in the plains can also occur in places like east of the Appalachians. And there's almost a mini tornado alley, a tornado potential in the eastern Carolinas, and that kind of potential extends right on up the eastern seaboard. Mostly moisture is the lacking ingredient when you get up into New England. You don't have the amount of moisture in the air available to sustain intense thunderstorms, but it can get up there, and it usually comes in the summer months when you have a real strong flow of southerly air from off the southeast U.S. seaboard. When the Bermuda High sets up and the humidity begins to increase, that's when you want to start to watch out for that potential in southern New England.
Great, thanks. Ruta writes and wants to know, what does a F3, F4, what does that scale mean? What's it refer to?
Failed to talk too much about that, and I should have put a slide in on that. The F scale was originated with Dr. Theodore Fujita at the University of Chicago. He was incredibly gifted and creative research meteorologist who really had a desire to understand these storms better, and he went about that by looking at the damage they produced. And so he came up with the scale, the Fujita scale, which really linked damage to strength. So at the time, and even to this day, it is very difficult to get an instrument in a tornado. One, they're very small scale, and two, if they're intense enough, the instrument won't sustain the wind speeds, and it'll be destroyed. So he looked at damage to structures like houses, and a weak tornado isn't going to do a tremendous amount of damage to a house. It might take off a few shingles, broken window maybe. A stronger tornado might knock down a wall or take the roof off, and he developed this scale of increasing wind speeds or increasing damage that was witnessed in tornadoes, all the way up to over 200 miles an hour for F5, Fujita Scale 5. In the 2000s, the wind engineers started looking at this scale, and also meteorologists, and decided to bring a little more stringent math and science to the scale, and they brought engineering experience to the scale and said, okay, if we know something about the structure that was destroyed, we can say, with more accuracy how strong the winds were, and that became the development of the enhanced Fujita scale, which we use today. There really isn't a big difference in the wind speeds. They adjusted some a little bit, but for example, EF1 tornado is about 100 miles an hour. An EF3 tornado, you're getting up over 150 miles an hour, and the EF5 is still the most intense with wind speeds over 200 miles an hour.
Greg, Tom writes and want to know if there's a breakdown of the F1 through F5 for each year, and if possible, is that available on the web? If it is, we can put it on our website. If that is, you can send that to me, and I'll be sure to put that up. There
are a variety of sources out there for this information. I can't point to one right now. I know I've done the chart over and over again, and I'm not sure if it's up on our website. I know the National Climate Data Center also maintains some information about F-scale ratings over the years. One thing we found when we look at tornadoes, say over the last 60 years and the F-scale, we've seen this tremendous increase in tornado reports, but mostly those reports are the weak tornadoes. And in the last 2 decades, the last 20 years or so, over half of the tornado events are of F0 strength. They're 80 mile-an-hour winds, not very strong and not all that dangerous really. When we look at F1 and stronger, or EF1 and stronger tornadoes, they're pretty consistent. We're seeing roughly a couple hundred of those per year. Some years many more than others, but if you did a trend or an analysis on that, very little change in the number of F1 and stronger tornadoes in any year. So when you see the plots, it's kind of interesting. And it's very informative to do that kind of plot where we're looking at the differences in F-scale and totals per year. I'll try to track that down and get a link to you.
That would be great. Mary from Wisconsin wants to know if are water spouts similar to tornadoes? Do they form over places like the Great Lakes, and do they continue over land, or does the land stop them?
That's a great question. And the short answer is that water spouts are not usually the same as tornadoes, especially in the warmer climates. Along the Gulf Coast and the Atlantic coast, water spouts are not all that uncommon, especially in the summer months. And they're really caused by rapidly rising air associated with thermals that form very close to the coast or on sea breezes. The moisture is already there because you're over the warm ocean or Gulf water, and during the day, as you get heating, the air rises so quickly that you'll form these spouts very quickly, not associated with what we typically look for tornadoes, and especially violent tornadoes, a supercell. They're not associated with supercell thunderstorms. In fact, they may not even have a thunderstorm associated with them at all. So they are kind of a different animal, so to speak, and they can form over lakes and usually dissipate. If they're not associated with a supercell, they're usually going to dissipate not long after they move over land.
Thanks. Here's one from Ed in Nashville. He wants to know if hail can predict the formation of tornadoes.
And that's another great question. And I would say that my answer on that is yes. I've often seen where very large hail, and we're talking baseball and larger, baseball grapefruit size, softball sized hail, can precede a significant tornado event. And if you look at the classic model of the thunderstorm, you'll often see this core of very, very heavy precipitation and the potential for large hail that is out ahead of the hook echo that we see on radar. And the hook is associated with the actual tornado. But the large kidney bean shape that you see on radar with all the heavy precipitation occurring can often contain hail. And if the storm is moving in the right direction, you could go through that heavy precipitation with large hail, and then it could be quickly followed by the tornado. So anytime you experience very large hail in an environment favorable for tornadoes, you want to be on the lookout.
Great, and I have another one here. Ben in Florida wants to know, is there any practical studies in attempting to diffuse these storms that produce tornadoes?
We always get those questions, or we always get actually the solutions, but I'm not aware of any. And when you think about it, I suppose if you could come up with a way of generating a tremendous amount of cool or cold air near the base of the thunderstorm, you probably could somehow cut off the moist, warm air that's required to sustain the updraft to produce a tornado. But I don't know of any modern engineering that is capable of producing that amount of cold air on such a scale that it could make a difference. And occasionally we'll get the email, too, about why don't we shoot missiles into these things, and well, that just doesn't seem to make sense because there'll be damage from the missile, but they're not easy to stop.
Okay, Chance from Indiana, and also Steve write about tornado watches. So Chance's question is, how long does it take SPC to issue a watch once the decision is made to do so? And then Steve, on a similar question, wants to know how long does a typical watch last?
Typically, the watches are out about 6 to 8 hours, and the process is an interesting one. We collaborate every watch with the offices in the field. So if we're issuing a watch across parts of Kentucky and Indiana like we did today, there may be 3 or 4 or even 5 different National Weather Service forecast offices that will be responsible for warning for any severe storms in that watch. And so the collaboration process is probably the one that takes the longest amount of time in the whole. If we didn't do that, we could probably have a watch out in a couple of minutes. But the collaboration involved can sometimes take 15 minutes or so. But from the point at which the lead forecaster makes a decision that a watch is needed and that the actual official watch is issued, I'd say on average we're talking no more than 10 minutes.
Kathy wants to know if any major cities have ever been hit by tornadoes, New York, Chicago, etc.
Yeah, Oklahoma City, Omaha's been hit, Huntsville, Alabama's had numerous events. And so cities are not immune, and the modern sprawl that we see occurring across the country with development on the outskirts of cities expanding is setting us up for even more damage. And so we almost seem to have increased our vulnerability in some parts of the country with respect to tornado events, because the more of a footprint we have, the more likely it is a tornado is going to strike that area. I don't want to see that happen, but unfortunately, again, there are a number of large cities. Just last year, we saw the Dallas-Fort Worth area come perilously close to having a tornado move in to Dallas, and then a few years before that, we did have a tornado move into Fort Worth. So there are many locations where a lot of people are concentrated where tornadoes can have an impact.
Okay, we're getting a lot of questions here. Here's one. Do tornadoes usually move from southwest to northeast, writes Janet. I remember the one here in Fort Collins, or just east of us, the Windsor tornado went from southeast to northwest. So what's a typical pattern?
That was an unusual day. I remember that tornado, and yeah, the average motion, and you can go back through the records over a long period of time, is southwest to northeast, and that's just generally the way weather systems move, in the country. Move from west to east on average, but the wind shear and the conditions that sustain thunderstorms, those ingredients we talked about, have certain configurations, at least geographically, how they're set up, and that you have very strong southeasterly winds in the low levels, topped by very strong southwesterly winds aloft. And it's really those southwesterly winds that are what we call the steering currents for storms. And so in a general sense, you'll see tornadoes moving southwest to northeast. Now the winds are one, and also one of the more unusual and violent tornadoes this is the last decade or over 12 years now, is the Gerald, Texas tornado, which moves southwest. Very unusual motion, and that was associated with the fact that there was a very strong boundary, a very strong demarcation between a warm, moist air mass and a cooler air mass, and the thunderstorm became anchored on that boundary and basically propagated southwestward, and the tornado formed and also moved in that direction. But that's very unusual.
Robert in Alabama writes and wants to know, does the data obtained by storm chasers enhance SPC's predictions?
Predictions, probably not so much, but situational awareness is critically important, both at the Storm Prediction Center and at the field offices that are responsible for warning for tornadoes. So I would like to say we can never get enough ground truth information. And so spotters, especially trained spotters who are working within the construct of Skywarn and the National Weather Service, spotter networks are crucial to real-time situational awareness, and that that kind of feedback is important during an event. If you've issued a watch or you've written a discussion about how you think the atmosphere is going to evolve, and you're not hearing anything, you begin to have doubts about whether your prediction is correct. And so it's critically important to have that information coming in on a real-time basis.
Okay, Matt in Wisconsin wants to know if you could talk about any impacts from global warming on seasonal tornado predictions.
Well, it's interesting that he'd ask about the climate change and seasonal prediction, because I think our foray into seasonal prediction is partly based on trying to understand climate change and its impacts on severe weather and tornadoes. One thing that we have seen in the long-term record with respect to significant weather events is there has been a noticeable increase in the number of extreme precipitation events globally. And that just makes sense. In a warmer climate, the atmosphere can hold more moisture, and so you're going to see extreme flooding events probably more likely. And people say, well, what about long-term drought? Well, the interesting aspects about a warmer climate is that you can have extremes of both magnitudes, and they can occur perhaps more frequently. When it comes to tornadoes, the jury's still out. There is not a clear signal in tornado data that would suggest that there's a change one way or the other. And I talked earlier about when we look at the F1 and stronger tornadoes in the continental United States over the last 60 years, we see no trend whatsoever. We do know that variability from year to year and month to month can be impacted by things like the El Nino Southern Oscillation and other larger scale climate oscillations and signals in the atmosphere. So there is linkage there, but it's not very strong linkage. And so what you're trying to do is go from a very large scale oscillation in the atmosphere to something really relatively small scale like a tornado. And that is not easy to do, and it's not easy to be scientifically robust with that type of analysis. So what we think we can begin to do is see how these oscillations impact tornado days and tornado events. And there's some very interesting early findings that we're starting to see with that, but we're not seeing a trend in more or fewer tornadoes. We may be seeing a trend in more productive days followed by longer periods without tornado activity. And we can't quite explain why that's occurring, but we're working on an article for Science Magazine on that.
Okay, Jerry wants to know that are dust devils similar to waterspouts more than tornadoes?
They are, in the sense that what's really driving a waterspout is the instability or the lapse rate difference in very warm air rising rapidly. And so the same conditions with dust devils. You have very, very warm air at the surface, and you have slightly cooler air above, and so you have this unstable condition. And even in dry weather, that's going to cause parcels to rise, and those air parcels, if there's enough dust around, the dust will be incorporated into that rising motion, and you'll see the swirls. But yeah, they're very similar.
Dave from North Dakota asks, what's the difference between straight line winds and tornadoes? He hears about them inflicting damage in parts of the country.
Well, as far as the damage goes, there can be maybe very little difference. And in fact, we saw an event last summer, at the end of June, with the what we call the derecho. And the word derecho is Spanish. It's the Spanish word for straight, just like the Spanish word tornado is the word for spinning or twisting. And so we use derecho to describe a straight line wind event. Usually these are organized thunderstorms in the presence of abundant, warm, moist air, but not necessarily the strongest shear. Enough shear to sustain some organization to the storms, but a lot of instability fueling that continuing development. And we saw that last summer, June 29th event, where it started with a single seed thunderstorm in northern Indiana that grew into a monster complex, a squall line of thunderstorms that raced east at 70 miles an hour across the Appalachians and into the mid-Atlantic region. And that's known as a derecho, or a severe thunderstorm squall line that spread for over 200 miles. No tornadoes associated with that. Now, I would say that occasionally we do get little spin-ups or tornadoes along the line, but they're not really associated with the classic supercell tornado. They're more these, vortices that just happen to coincide with the stronger winds associated with the line of thunderstorms. So straight line winds, much different than tornado. The other thing, when we're talking about winds, we can also have what are called microbursts, or downburst winds associated with a single thunderstorm, usually in the summer months where it's very hot, and you get one single thunderstorm can develop. And these posed a tremendous challenge for aviation over the years, where we've seen a number of aviation accidents due to individual thunderstorms having to pop up right over an airport and producing downburst winds that then the aircraft flies into and is pushed to the surface and crashes. There have been improvements in forecasting those and improvements of observational networks to try to detect those storms before they form and alert the aircraft in the area to wind shear. And so thunderstorms take a lot of different forms, and so do their hazards.
Jeff, a similar question. Wants to know, for Jeff from Missouri, what ingredients within a storm cause it to go from an F1 to an F5 in a matter of minutes? I guess, is it something to do with the rotation speed of the storm, or can you answer that?
I thought I was doing pretty good answering questions, but that one, that is an unanswerable one. There's not a lot known about what causes changes in tornado intensity. We know a few things on a large scale, but being able to predict actual changes in tornado intensity is very much it's an explored area, but the exploration of answers for that is not yielding too much. We know that wind shear plays a very crucial role in thunderstorm rotation intensity. So wind shear is a very important component, but you can get to a point where wind shear is too strong, and a tornado cannot form in such a strong environment given it's too strong. So there's this happy medium, and it's not just the shear, but it's the mixture, the ingredients of the instability and the lift, and so many other factors that have to be at just the right magnitude in order to sustain a tornado. And then, why do certain tornadoes dissipate rather quickly? We had an event yesterday in Oklahoma. Some of the top researchers in the world looking yesterday at the forecast and expecting, at least one significant tornado in Oklahoma yesterday. Very few of the storms produced much in the way of tornadoes. They all came together. There was a lot of thunderstorm activity, but it did not really result in very strong tornadoes. And so we don't know exactly why that was the case. We can make some guesses, but I can't point to any one thing and say, oh, this is why it didn't work out the way we expected.
Greg, how are you doing on time? Do we have time for a few more questions?
Sure.
Okay. We'll try to get maybe we'll go about 10, 15 more minutes if we can. We've got a bunch of them here. Robert asks, what is the difference between a squall line and a dry line?
Oh, okay. Well, a squall line essentially is a line of thunderstorms. So storms that form, whether it's on a cold front or ahead of a front, you just see a line of storms on radar, and they're moving relatively fast. Not necessarily, doesn't have to be severe weather associated with them, just a real rapid increase in wind speed and some heavy rain, maybe some small hail, and the line passes. A dry line, like the word suggests, is dry. There really isn't much in the way of thunderstorm development, at least initially on the dry line. And the dry line is a very interesting surface weather feature that shows up on the weather map starting about this time of year across West Texas, parts of southeast Colorado, up into western Kansas. And it's really the demarcation between the dry and warm air that comes off the high terrain and the plateau and the Rocky Mountain front range. That's coming down, and that sinking air is warming and drying, and it interacts with the warm, moist air that's coming up off the Gulf of Mexico, could even be coming off the wheat fields in the plains. And it turns out that as that heating occurs during the day, this discontinuity between air masses becomes really sharp. You can go across this boundary and just a few miles go from a relative humidity that's rather sultry and 65–70% relative humidity, kind of a very moist air mass, to an incredibly dry air mass where the relative humidity is down in the single digits. And so that's kind of defines the dry line, which sets up, because of topography and because of the way the wind is blowing around the surface, mostly in the high plains, southern high plains of the United States.
Bud says he lives near Lake Michigan, and there's a myth saying that the lake protects us. Is there any truth to that?
There actually could be some truth to that. The one thing that the lakes tend to do is generate a mass of stable air, because you've got cool lake water sitting there, and you know that the lake breeze sets up during the summer months. And once that lake breeze moves inland, you're in relatively stable air. It's cooler. Perhaps not as moist as inland, certainly not as unstable. And so if you're within the lake breeze or in that area where the wind is coming off the stable air of the lake, you're not going to be able to sustain a very intense tornado into that environment. Now, at the same time, that boundary between the stable lake air and the hot air on the other side of it, whether that's over Michigan or sometimes it sets up over parts of Wisconsin or northern Illinois, depending on what the wind is doing. But that boundary can often be a location where tornadoes would be preferred, because you've got a very favorable region there where the wind shear is favorable for rotation in the thunderstorm. And if it's incorporated into a thunderstorm updraft, that lake breeze boundary can often favor tornado development.
Great, thank you. Here's Ben from Florida wants to know, what do you mean when you refer to higher or lower heights at the 500 millibar level that are conductive to tornadoes? What does that mean?
Well, thanks for the question, and yeah, I wasn't sure how in depth to go there, but the meteorologists will use what we call the 500 millibar level, which is essentially the level of the atmosphere in which the pressure has reached 500 millibars, or what they call 500 hectopascals, and it's generally around 20,000 feet or so in the atmosphere. And when you look at those maps, you kind of look at them as contour maps. What you see in the atmosphere are waves. And you see some areas where there's more air over an area. When there's more air over your head, you're in high pressure. And when there's less air over your head, you're in low pressure. And so we look at the 500 millibar map, which is about midway through the atmosphere, and shows us where these waves are occurring, not really associated with anything at the surface, but they do drive weather systems at the surface. So the 500 millibar level is kind of one of those standard levels in the atmosphere that meteorologists will look at to try to better understand the three-dimensional nature. And so below normal heights are usually associated with less air over your head, and so lower pressure. And above normal heights are associated with more air or more mass above your location and higher pressure or sinking air. And really want to see a combination of those as the waves move through the atmosphere to generate weather systems. But sometimes you can get these stagnant patterns where you're stuck in a high pressure system or you're stuck in a low pressure system. And when I showed those maps from March, what it really showed was that we were stuck in a relatively low pressure area where there was a lot of air aloft, and it was also cooler than normal, because usually the lower pressure in the upper atmosphere is associated with cooler air. And so that, I hope that explains it. But that's what we're doing.
Great. I'm getting a lot of questions from folks asking if there's a PDF version of this slideshow that you might be able to make available to us to put on our website. Is that something you could do?
Yeah, I'd be glad to.
Okay. Okay, we'll have that up here as soon as we get it from Greg. We'll put it on the website. Here's Alex in New York, and he says, why do we see an affinity between trailer parks and tornadoes, a correlation there? Is there anything to do with that?
I think again, it goes back to the vulnerability problem. Most tornadoes are relatively weak. They're not going to cause too much of a problem if you're in a well-constructed home. However, manufactured housing and mobile homes are very vulnerable, even to relatively weak winds. 50 miles an hour, 60 miles an hour can roll a mobile home. And so even the weakest tornadoes pose some threat to mobile homes. And since we see many more weak tornadoes than we see strong ones, we see a lot of damage to mobile homes, and unfortunately injury and death too. Mobile homes are just not a safe place to be in tornadoes, and so we just tend to see where the damage occurs, and we see where they're particularly vulnerable.
I've got several questions here, several folks asking about the difference between tornadoes and downbursts or microbursts, and can they come from the same storm? Several folks want to know.
They can and they can't. A downburst, when I think of downburst or microburst, I'm thinking of an individual thunderstorm that may not be all that well organized. A tornado really requires a supercell thunderstorm. Now, a supercell thunderstorm can also have very strong winds associated with it. We call the rear flank downdraft of the supercell. Sometimes you may not get it. Many supercells don't produce tornadoes at all. They'll produce hail, and they'll have rotation, but not a tornado. And sometimes that rotation can be associated with very strong winds at the surface, but you never see or experience a tornado from that thunderstorm. And so, in some sense, the strong winds associated with the supercell could be considered a downburst. But when I think of a downburst, I'm thinking of a lone, relatively unorganized storm that happens in a hot air mass, and it's the evaporational cooling that occurs with the rainfall coming out of that thunderstorm that causes a cold bubble of air to form underneath it. And that cold air slams to the surface of the earth, because cold air sinks, and it sinks very rapidly, and it slams and hits the surface of the earth and then spreads out. And that's a downburst, and those wind speeds can be just as strong as an F2, F3 tornado in some events. And so people could get damage that certainly appears like a tornado event has occurred, but it could just as easily have been a relatively poorly organized thunderstorm with a downburst wind.
Okay, we're going to take a couple more. Jim has a very interesting question here. What is the safest thing to do if you're in your car when a tornado is in the vicinity?
That is a very tricky question, but a good question. And the first thing to do is try your best not to be in that situation. That would be one thing to do. If you think you have a pretty good idea of the tornado's motion, and you think you can, perhaps get away from where that tornado is going, then I would recommend you try to do that in the vehicle. If you think it's impossible to get away and that this tornado is bearing down on you, there are two possible actions you can take. One suggestion is, get the car off the road. I would look for a low spot or a ditch that you could get to. The lower, the better. There's some suggestions that you should stay in your vehicle. I think that's a rather tricky thing to do because vehicles can easily be lofted by strong tornadoes. The other suggestion is get out of the car, get to a low spot, and cover yourself. There really are no easy answers to that one, and that decision is going to come down to what you feel most comfortable with at that moment. To be honest with you, I'm not sure which one I would do, and it would have to be, spur-of-the-moment decision. Do I stay, with my seatbelt on and hope that the airbags deploy if the car is rolled or thrown, or do I get out of the car and try to get to some other safe place? Just no easy answer.
Yeah, Greg, I remember actually at night we were driving back from a ball game in Denver. It was a tremendous hailstorm. We had to pull over on the side of the road. The car was shaking. There was possible tornado in the area, and you really don't know what to do. I mean, the hail's beating down so hard outside. It is really tricky, especially at night when you can't see stuff coming.
Yeah, and you could, even without the tornado, you get out of a car in that situation, you could be pretty severely injured by the hail. And that would be a situation where, I'd probably stay in the car.
Okay, we're going to take about two more here. Several folks have also written about gustnadoes. What are they? They've heard of them. Is it like a dust devil? Is it a tornado? Gustnado.
Well, the atmosphere's got all sorts of instabilities and swirls and whirls going on all the time. And, we see this in what we call the leaf devils, when you see leaves spinning around in your front yard or in your driveway on a blustery day. The atmosphere generates vortices on all scales all the time. And I was talking to a longtime researcher into tornadoes 2 summers ago. He happens to live in Vermont, and I wanted to go visit him. He wrote the book Significant Tornadoes, where he documented U.S. tornado events back into the 1700s. And he estimates that there may actually be upwards of 20,000 tornadoes a year in the United States. And I said, no, I was just sort of looked at him with my mouth agape saying, what do you, oh, no, I don't want to count any more. Thank you. But I think what he was referring to is that, it depends on how you define a tornado. I tend to use the strict definition of a violently rotating column of air in contact with the ground. The key word there being violent. Dust devils, leaf whirls, steam devils, most waterspouts are not really going to be all that violent. And so, yeah, there's a certain spectrum there where they may begin to enter what you would call a tornado. But I'm not counting the leaf devils yet. And I think he said that, if we really could see all of the vortices going on, there's maybe more than 20,000. So the atmosphere has a remarkable array of circulations associated with it.
The book you mentioned there, I'm trying to remember the title of that. That we could put that on our website as well for folks.
It's Significant Tornadoes. Yeah, I don't think it's in print anymore.
Okay.
But it's an amazing book. We call it The Big Green Monster.
Yep, I remember seeing that in one of the offices here. Actually, I'm reading a book right now, very interesting, called Storm Kings by a guy named Lee Sandlin, looks at the America's First Tornado Chasers, and if you guys get a chance, it's pretty interesting on that stuff.
Yeah, I have to check that one out.
Yeah, I'll put that up on the website as well. Okay, let's take, this will be the last question of the day. This is a good one. Marjorie from Iowa wants to know, has dual polarization radar made a big step forward in identifying tornadoes on the ground?
We don't know yet. I think that's the answer I would give. There have been some very interesting developments with dual pol. We now can, in addition to seeing typical traditional radar, really gave us the information about the precipitation and particles within weather systems. We added Doppler radar. That gave us the ability to detect the wind speeds, at least along the radial, which direction these particles or rain droplets or cloud droplets were moving. And now with dual pol, you have another dimension where you can begin to interpret the shape and size of some of the particles. And there's indications that debris associated with tornadoes shows up quite dramatically on some of the dual pol imagery. But I don't think enough verification of this signature has been done yet to equate it with an actual tornado event. You could have strong winds produce debris, leaves and branches could be lifted around a particularly strong thunderstorm, and you may see a false alarm of these signals. However, it's another dimension. It's another look into the atmosphere that should ultimately provide better service and better warning before these events.
And for those of you folks out there who don't know what dual pol radar, that it's just been, I guess at all the Weather Service offices, they're all going to that now. Greg, could you just briefly touch upon what dual pol is for folks?
Essentially, typical traditional radar sends out a beam of energy in one, it sends it out around the radar site, but in one plane. You think of it in a 1D, sort of along the horizontal plane. This pulse of energy goes out, and it returns to the radar along the same plane. What dual pol does is it sends out two pulses, and one is along the horizontal axis, and the other pulse of energy is oriented along the vertical axis. And the electrical components of the radar can decipher the signal. Don't ask me to tell you how, but there's some remarkable electrical, physical equations that are used to decipher the return signal and the change in the signal's polarization that can give insight to the meteorologist about the size and shape of the water droplets, or whether you're talking about hail or snowflakes within a storm. And so this is just another way of looking, another dimension of looking at the atmosphere. I've often compared the Doppler radar with a CAT scan of the atmosphere, which is sort of what it is. And now with dual pol, we're maybe getting to the MRI of atmospheric sensing.
Greg, I'm going to take one last question. We missed this one earlier. Mrs. Metcalf's second grade class is listening in, and they may have missed this earlier, but if you could just tell them which states have the most tornadoes is their question.
Sure. Well, Texas takes the prize, but that's really no surprise because it's got so much area, and it's in that favorable area of the country which sees tornadoes. So by size, it's really Texas. If you were to try to adjust for size, it's probably Kansas in the long term. Kansas kind of takes the prize as being one of the more common areas of the country where tornadoes occur.
Great. Well, thank you so much. We really appreciate your time today. This is fascinating talk. We've got a bunch more questions. We can go on for probably another hour or two with these. There's some really good ones. Greg will try to answer those offline for you over the next week or so if he gets a chance. He's a busy guy, but hopefully.
I would also recommend that on the Storm Prediction Center site is the frequently asked questions. And Roger Edwards, one of my colleagues here at the Storm Prediction Center, has done a great job on that website. And so you might find your answer there before I can get back to you.
Well, great. Thank you so much. We'll be posting these other things later on today. And we wanted the folks out there that are still online, we wanted you to know about our next CoCoRaHS Weather Talk webinar. That'll be coming up on May 9th in a couple weeks. It'll feature Jim Fleming of Colby College in Waterville, Maine. And Jim is going to talk about history of meteorology. He's going to talk about the emergence of the new interdisciplinary field of atmospheric science in the 20th century. It's shaped by different technologies. He's done some great history stuff, and hopefully you'll be able to tune in for that. Greg, thanks again for being with us today. We're going to ask folks as they leave the webinar now if they will complete the survey at the end of today's webinar, and that will help us a lot. So this is Henry Regis and the rest of our crew here from Fort Collins, Colorado, saying have a good afternoon, and we'll see you on our next webinar. Have a nice day. Bye-bye.